This is the water tower design presentation of William Van Kuren and Zebulon Winfield. We'll be going over our location, design process, and design implementation with some behind the scenes on our design report.
So much of America struggles with water scarcity, especially in areas with few above ground water sources like lakes and rivers. More rural places that have acres of farmland are heavily dependent on external water supply for the integrity of their infrastructure. However, if the towns should endure something like a crisis in water supply, there's not a lot of places that would be prepared to be self-sufficient. One such town is Magdalena, a small town in central New Mexico. And Magdalena had a terrible water crisis in 2013 due to drought that led to water relief efforts being made. This is hugely expensive for the government. And as climate gets less and less predictable, and the government spends more and more on relief efforts elsewhere due to hurricanes and other natural disasters, small towns may be left to fend for themselves during times of crisis. Additionally, Magdalena competes with nearby farmland for groundwater supply, meaning the town will take second priority in times of crisis. For this reason, we believe Magdalena would benefit from a water tower that could support the population in times of shortage. We decided that the town of Magdalena would be a good spot because it has a large mountainous region to the south. It's the Cibola National Forest. But even though it's a national forest, there is a part of these hilly forests that exists inside of the county limits, allowing for building permits to be secured. The water tower could be built in these hills, so the extra elevation could aid in the distribution system of the water to the town. And then for the Christian perspective, I'm going to quote a verse from the Gospel of Matthew, chapter 25. And the king will answer them, "Truly I say to you, as you did it to one of the least of these, my brothers, you did it to me." In an area of poverty and water scarcity like Magdalena, the survival of its citizens is under threat during dry summer months. God calls us as Christians to help those in need, those the world would call the least of us. And when we do so, we are helping Christ, as we are all made in God's image. For this reason, Water Tower is an act of charity and mercy on those who struggle to pay for water when it runs low and the bills increase. Not only is it helping the less fortunate, but it is also helping the earth. Genesis says that we are stewards of the earth, with dominion over its lands. As such, we will desecrate the earth. We desecrate God's creation in rebellion of his will. When we dig deeper for groundwater, we are destroying resources that are not easily renewed, whereas the collection of rainwater is much less harmful to the earth. As such, creating a water tower, a more environmentally friendly and sustainable source of water, is Christian stewardship of the earth.
So now to shift more into the design of the structure itself, the two truss designs we chose to go with were the Pratt and Howe truss because their simplicity first and foremost. They're both simple designs and they are actually opposites of each other, where the Howe truss has vertical members in tension and diagonal members in compression, and the Pratt truss has the diagonal members in tension and vertical members in compression. Our hypothesis was that the Pratt truss was going to be more efficient because the diagonal members being in tension, would allow for a better load distribution because we had a very wide base and a shorter height, which would lead to longer diagonal members. So the tension would be better in that case. The water tower had to be very wide, the water tower itself, because the area does not get a lot of rain, with only 9.4 inches a year. The tower must also hold enough to allow the use of 200 gallons a day from the town, with the constraints of a maximum radius of 45 feet. We decided to go with that maximum 45 feet and a height of 6.167 feet to hold enough water to be 200 gallons a day or 276,000 liters a year. Rainwater alone in this climate would not be enough to support this criteria, but we made the tank tall enough that it could support the 200 gallons a day if water were to be like shipped to it. So it could hold that 276,000 liters. We didn't want to make it any taller than necessary to hold that minimum because it would add extra weight to the tower, especially full, which we were worried our truss may not be able to support. And for the hand calculations, we used the method of joints in both designs. We first found the support reactions for a pin and a roller. A pin and a roller are used so that it is statically solvable. If we use two pins, it would not be. And additionally, that would create a lot of stress inside the structure without it being able to move. So we found the restraints, calculated the equations for each individual member in terms of W and F for the weight and force respectively. Then those equations were plugged into Excel with the values for W and F at the average wind speed and full tank, average and half tank, double speed, half tank, double speed, full tank.
So the designs were both created in SolidWorks in 2D using Weldman's tools and static analysis to simulate the load and restraints. All joints were restrained on the Z-axis to simulate a 2D dimensional truss and to prevent deformation or forces acting in any direction other than the X and Y axis. Then different simulations were run with the same variables used in the hand calculation section, and the results were put into Excel with the hand calculations. Finally, a percent error was calculated to measure the efficiency of both methods. The largest drawback of this method using 2D is that it simulates the perfect condition of a centralized point load instead of a distributed one. So a more realistic analysis couldn't be conducted. This was what the 3D design could help fix. When designing truss A in 3D, we came across an issue where it didn't matter whether restraints were placed, what matter the truss was made of, how small of a load was applied, whether the load was distributed or centralized, the order of the weldments were set up, or the size of the trusses, the structure would just not restrain, leading to the image seen on the right, where the static body was not static. The stress analysis on the left seems to be working as intended, but because the deformation analysis was just really unreliable, it was assumed that the whole 3D analysis was unreliable and it was scrapped for the entire project. This was not a decision made lightly, as many hours of troubleshooting was spent exhausting every single option, every YouTube tutorial, professor suggestion, and AI recommendation before it was simply decided to only include the 2D design in the project. This has the drawback of disallowing a more accurate analysis with simulated distributed loads that show the actual stress and deformation of both structures to draw more accurate conclusions. Instead, an inference on stronger structure would have to be made based on the 2D analysis.
And now to shift into the winning design. So if a 3D analysis of both structures could be obtained, it would have been the main method of choosing the better structure, where the choice would be based on effective distribution of loads, the highest force experienced by any one member, the least deformation, and the price of the overall materials. The 3D approach could then be used to determine the best type and size of truss as well. But because we do not have the 3D analysis, the same criteria, the distributed loads and force, etc., would be applied, but using the 2D models. So it's harder to decide on the shape and size of the trusses themselves, but we could research that online instead. Based on this criteria, truss B would be chosen. This actually disproves our initial hypothesis because truss B was the Howe truss. As the load at the center of the joint was a better spread between 5 joints rather than the 3 joints of truss A. This leads to a more even distribution, and a smaller deformation with 110 millimeters in design A as the maximum deformation and 43.5 millimeters, which is less than half the deformation in design B, and that's at the maximum weight and wind speed. However, the actual design process was a little different. Only one structure, structure A, was completed in time with the SolidWorks simulations, hand calculations, and percent error calculations before the due date with enough time to complete the remaining tasks. So it was chosen by default. If both structures were completed, structure B would have been chosen as outlined due to pretty much every mode of the criteria for selection: the improved load distribution, smaller maximum force experienced by any one member, less deformation, and less materials used overall. And although some might see it as a bad thing, we see it as a valuable lesson that can be applied to all real-world project management. Whenever an idea, product, project, or otherwise is being pitched to a buyer, it doesn't matter how good it is if it isn't available by the deadline.
With that being said, we're now going to get into implementing the actual design. So the two choices were made going from the initial design to the final selected design, where the types of restraints and the size of the truss, where the thickness of the tank had already been calculated to find the weight of the tank for calculations. It was decided to put only one roller joint instead of two diagonal from each other. Having two diagonal from each other would make it more accurate to the 2D design because each face would have one roller and one pin. But with one roller and three pins, it allows for more capacity for horizontal restraining, while still allowing the truss structure to bend and flex as temperatures and loads change. We think this middle ground gives us the best restraining capabilities while also stopping any possible collapses due to internal stress caused by too much restraint. The truss shape and size was decided earlier in design when attempting to create a 3D model after some research, when it was found that a rectangular tube would be most effective with a large vertical load, and the 8x4 by 0.5 inch tube pricing was very researchable and affordable, both necessary for the bill of materials, while also being large and thick enough to support the structure. This was only decided through research, though, because further analysis could not be conducted through the 3D SolidWorks analysis. All numbers are averages from various construction websites and the use of conversion equations with amounts roughly estimated from the assembly instructions and detailed drawing. For this, the steel price is the approximated price of steel for the tank based on our measurements. This does not take into account the price of manufacturing the tank, nor do the man-hours section include manufacturing the tank. So the steel price represents the price of the tank as a whole, which is why a price of $0.33 per pound was used, which may be a high estimate for the bulk construction price of steel for a large construction firm to account for production costs. For that reason, estimates might be low. Other estimates include that a 6-man construction crew could complete the job in 1 work week. The welder could complete his task in 2 work days, and we would only need the crane and crane operator for 2 work days.
So after this project, there were some key takeaways on what we could do differently for future projects or the same project done again. The first and most obvious is time management. If we had 2 completed trusses to choose from in the design selection, it would have improved our final product. Next is the 3D modeling. Although ideally it would be nice to have a fully functional 3D design for a future project or this project, if unforeseen hiccups happen like they did in this project, it could still be beneficial to investigate how the different truss sizes affect the stress, because it seemed that the stress graphs or stress analysis was still functional for the 3D SolidWorks design. Although this couldn't be taken with as much authority as the a fully working 3D model might be or might shed light on it, the partial 3D design would still help in choosing a final product, as it would show what the stresses would be with a distributed load in a more realistic environment with all 4 faces. Finally, choosing a location that gets more rain would be an easier task for water tower production, because the current location made us choose a very wide design, which created a lot more stress on each individual member. And that could be circumvented if a taller tower could be made in an area with more rain. Realistically, if an above ground water source was to be created for Magdalena, it could be created without any truss, just in the mountains because of the elevation above the town. So with that, that concludes our report.
Thank you so much for your time, and yeah, have a good day.